think the molecule likes to be anti-aromatic, or would it like to somehow avoid it? It would like to avoid it. How does it avoid it? This is it. It just goes. And now it's no longer planar, and now the p orbitals no longer line up. Game over. It's not a cycloconjugated system, so it's non-aromatic. The molecule can easily just pucker to avoid this. By the way, if it was planar, and if you can remember your 9th grade geometry, that bond angle is greater than 120. You can actually see, you see the strain of that bond, how it's kind of bent up? Whenever we go to the tub-shaped, I want you to look at this bond. Everybody can't see it. But right now it's kind of strained. It's like, we go tub-shaped, it's no longer anti-aromatic because it's not cycloconjugated. But also, look at that bond now. It's no longer strained. That's 2 reasons it wants to go tub-shaped. So in actuality, this is not a cycloconjugated system. Huckel's rule assumes what? Huckel's rule assumes you're dealing with a cycloconjugated system. But you might not be. So you have to know what type of properties you expect. This compound, heat of hydrogenation, is just 4 pi bonds. Okay. Any more questions about those? Any questions about anything we've covered this far? We'll start with, pick up here, anions and cations. How about this compound? Aromatic, anti-aromatic, or non-aromatic? Good. Why is it non-aromatic? Well, that's the same answer for any non-aromatic compound. A non-aromatic compound is non-aromatic because it's not a cycloconjugated system. Does it have p orbitals all the way around? No, there's no p orbital here. The carbon's sp3. No p orbital. Game over. What about this compound, though? Aromatic, anti-aromatic, non-aromatic? Yeah, it's aromatic. Why? Well, if I'm telling you it's aromatic, that means what? That means it's a cycloconjugated system with 4n plus 2 electrons. And that's why. But the question really is, do we understand why it is a cycloconjugated system and 4 pi electrons? 4n plus 2 electrons. What's the hybridization of this carbon here? The carbanion. Hybridization? Camille? sp2. Yes, it's sp2. Okay, so what is that going to look like? Let's draw an orbital diagram of this molecule. And for some reason I like to turn it sideways. I'm not quite sure. I think it's just easier to draw. I'm going to turn it sideways here. Now, pi bond here and here, right? And then that's the anion there, okay? Pi bond is made up of p orbitals overlapping, one electron making pi bond. And then down here we have one electron making pi bond. There's your 2 pi bonds. Here and here. Now we're going to say this is sp2. That means what's the geometry of this carbon? Trigonoplanar. There's your trigonoplanar. You see how this is trigonoplanar? Bond angle is 120 all the way around. Okay, what else is on this sp2 carbon that I haven't shown yet? Dominique? Well, 2 electrons, but what other type of orbital? I'm showing 3 signal orbitals here. What else is here? Valerie? P orbital, right? I mean, it's an sp2, 3 hybrids and a p. They're your hybrids making your signal bonds and then a p. Okay? What is in what is in this p orbital? Lone pair? Yeah. And that p orbital can interact with that one? Is that a cyclic conjugated system? Five p orbitals all the way around, as long as they're indeed lined up like toy soldiers. Yes. Cyclic conjugated system. Does everybody see that? We did lots of this scenario in Organic 1. If you graph this carbon here, what would it look like? sp2, graph it. We have 3 hybrids and a P. What does this bond to? I mean, what is that carbon bonded to that's not shown? Yeah, that's bonded to an H, right? A carbon, sigma bond to carbon, sigma bond to carbon, sigma bond to H. Sigma bond to carbon, sigma bond to carbon, sigma bond to H. Where are the other 2 electrons? P orbital. How many valence electrons? 1, 2, 3, 4, 5. But carbon's only supposed to have 4. It's got 1 extra. Well, that's why it's a minus charge. There we go. How many pi electrons in the pi system? How many electrons in the pi system? 1, 2, 3, 4, 6. So we have a cyclic conjugated system with 6 pi electrons. What does that mean? Aromatic, right? Aromatic. That's 4 n plus 2. This is an example of an aromatic anion. Because it's aromatic, it's relatively easy to form. You can take this guy and treat it with hydroxide. And you can remove an H to get this plus water. And the pKa of this, is it listed somewhere? Well, it's shown below. pKa is about 16. That's a hydrocarbon with a pKa of about 16. Usually hydrocarbons have pKa's more like 30 and 40. Why is it so acidic? Why is it so willing to lose an H? Because look where it's going. It's going to an aromatic. It's like, I don't mind losing an H. I'll be aromatic. Take my H. Please. Understanding aromaticity allows you to understand why this is much more acidic than the usual hydrocarbon. How about the one over there on the right? Aromatic, anti-aromatic, what? Is it a cyclic conjugated system? P orbitals all the way around here. Can we imagine this having a P orbital? Yeah, it's just like this here. It's just like this here, except we slipped an extra double bond in. We may have to modify this though, because I just realized that was 6, and this is how many? 8. This is a cyclic conjugated system with 8 pi electrons. Is this going to be aromatic? Anti-aromatic. Hold on now. If planar. By the way, we should do an MO diagram for one of these and just affirm that we know how to do that and see result. Question, do you think this guy wants to be planar? Why did this prefer to be sp2? So it can be aromatic. Is this one going to want to be sp2? No. It's probably going to remain sp3. With no p orbital. And if it has no p orbital, what would it be? Aromatic, anti-aromatic, or non-aromatic? Yeah. This compound's probably non-aromatic. There's actually very few anti-aromatic compounds because usually if they can avoid it, they will. See, instead out here, this carbon is probably lone pair and H. In a tetrahedral arrangement with no p orbital. Because of that, if we drew the just a neutral compound, do you think this guy is as acidic as this guy? No. This has a pKa of greater than 40. That compound is like, I'm not giving up my H. There's no stability here. That's just a plain carbanion, isolated. That's no more acidic than like hexane. Let's do a molecular orbital diagram for this one here. Questions on these two? Uh-huh.
We're just going to let you use as to how the third one is likely to be sp3, whereas the second one is very similar but sp2.
This one's more likely to be sp3.
Could you explain why?
Well, if it was sp2, it would be anti-aromatic. It's like it has a choice. Do you think this one wants to be sp2? Not if it's going to be anti-aromatic. But this one does. If this one's sp2, it's aromatic. Cycloconjugate system with 6 pi electrons. If we do the same thing over here, we would get this cycloconjugated system with 8 pi electrons. But that is an anti-aromatic arrangement. The compound doesn't want to be that. It's just like conformations. I mean, if a molecule can be anti or syn, which one is it going to prefer? Syn? Sorry, anti? Why not syn? Why anti? Lower energy. So which is lower energy? Anti-aromatic or non-aromatic? Non. So anti is worse than. So instead, it adopts an sp3. Instead, we have it. If it's sp3, is there a p orbital on this carbon? No. If there's no p orbital, it's not cycloconjugated, and game over. It's non-aromatic. That compound would prefer to be non-aromatic rather than anti-aromatic. Molecular orbital diagram here real quick. Let's see. How many p orbitals in the system? Yeah. 5 p orbitals with 6 pi electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4. Hold on, we got to put one more pi electron up here. Put it anywhere you want. Let's put it here. Yeah. See, this is your lone pair. One of the p orbitals has a lone pair. The others have 1 electron each. It's sort of our starting point, right? Okay. Nothing new than what we've done before. 5 p orbitals. How many MOs are we going to make? 5. Now, the best one is going to have the orbitals interacting constructively all the way around. It's going to be low. It's going to be 1. Let me do it over here real quick. It's going to be 1. As I said in the guidelines to MOs, it's 1 and then 2 until you run out. Well, I ran out because there's 5. The midline goes through here symmetrically. Now, when you have an odd number, how do you go through symmetrically? It's really symmetrical in terms of energy. The midline comes through here. So it's 1, 2, 3, 4. So the midline coming through here. So I just repeated this over there. There's your setup. How many electrons do we have to put in here? 6. 1, 2, 3, 4, 5, 6. What do you see? Are all electrons paired, or do we have a diradical? All electrons paired. Well, we knew that because anytime you have a 4n plus 2 number, all electrons will be paired in your MO diagram. That's Huckel's rule. Questions about this MO? We can add details to this. For example, if you were to draw these MOs, how many nodes would this one have? 0. And this one? 1. And that one? And now that we know where the midline is, what type of MOs are these? Bonding, bonding, and that one? Those are anti-bonding, but they're empty. What do you want to call this level here? Any particular name? It's the highest occupied molecular orbital, right? What do you want to call it? HOMO? What do you want to call that one? LUMO? Do you understand why this is symmetrical through here? No. 3 below, 2 above? It doesn't look symmetrical. What's symmetrical is the energy. The energy down here is the same as the energy up here. For example, you put your pencils down. It's extra information here. How can we get 3 and 2 here? I think we can maybe get it this way. I'm just going to try to illustrate what's symmetrical. If this is -4 and this is -2, some arbitrary number. This is 4 below the midline. This is 2 below the midline. What is this a total of? 1 is 4 below, and you got 2 that are 2 below. That's a what? That's a net of -8. Arbitrary number. What has to be the same is above has to be +8. How do you get +8? What are each one of these going to be? Yeah. So above is going to add up 2 of these at +4 equals what? +8. That's what's really symmetrical. So when you have an odd number, okay, so let's don't worry about it anymore. But that's sort of what we're talking about with symmetrical. Question?
Yeah, how do you know it's not 3 above 2?
Hey, no, it's not what?
3 above 2.
What do you mean, +3 here?
No, I'm talking about the amount of space. Why did you put 3 on the bottom there with all the electrons and not
As
3
opposed
on
to
top?
what?
3 on top. 3 lines.
How would you get 3 on top?
I mean, you drew a line through the midway point. You're saying this is symmetrical, right?
Are you saying draw the midpoint through here? If we drew midpoint through there, it would be 4 on top, 1 below.
No, I'm saying put the bottom one, the very bottom one, up on top. Why is it not that way?
And go 2, 2, 1?
Yeah.
Okay, well, let's look at that. 2, 2, 1.
Yeah, and
Well, look what you've done. You're saying there's 2 ways to...
you'd rather put everything on the lower energy, is what you're saying, right?
There's only one way to have them all overlap good. There's always only going to be one at the bottom. Well, there's only one way to have plus, 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 plus.
Yeah. Okay.
You always have one at the bottom. Again, if you start with 1, you go 2, 2, 2 until you run out. You may end up with 1 at the top if it's if you got 1 left over. Okay. Let's look down here. These are obviously carbocations. This guy is obviously non-aromatic, right? Because there's no p orbital. What about this guy? We draw, I'm going to draw in the orbitals here. I mean, you see that pi bond there? That's what the pi bond is, right? Because it's kind of turned, and really all these are coming out. Of course, that's overlapping too, and that's overlapping. What do we have here on this carbon? Is there a p orbital? What's the hybridization of that carbocation? Carbocations are sp2. That means it's got a p orbital. And now that it has a p orbital, what do we now have here? All the way around. Cyclic conjugated check. To be cyclic conjugate, it doesn't matter how many electrons you're dealing with. We're talking about p orbitals. Does that molecule have a p orbital all the way around? How many pi electrons in the system? 1, 2, 3, 4, 5, 6. Anything in this p orbital? Okay, we have a cyclic conjugated system with 6 pi electrons. What do we have here? Aromatic. That's an aromatic cation. Everybody should know hybridization of a carbocation from organic 1. It's right? Do we need to graph the hybridization of that carbon? Why is it sp2? Precious, why is it sp2? Okay, it's bonded to those 3 things. Why is it sp2? Eddie? Those has 3 bonding regions around it, and those are best spread out trigonal planar. Yeah. If we graph that, so we're immediately going for sp2. If we graph that, sp2 means it has 3 hybrids, and what's left over? P orbital. What type of bonds did you say you see, Precious?
Carbon,
Bond to carbon, bond to carbon, bond to hydrogen. There you get 3 sigma bonds that you just described. What's in the p orbital? Absolutely nothing. Empty. I only see 1, 2, 3 valence electrons for carbon. It's supposed to have 4, so we got a charge. It's missing one. What's the charge? Plus. That's why it's a plus. That's an empty p orbital. Right there. It's empty, but it's there. And now we have a cyclic conjugated system of 1, 2, 3, 4, 5, 6. Nothing there. We have an aromatic carbocation, an aromatic cation. Now here the 7-member ring cation is aromatic, but the 7-member ring anion was anti-aromatic, but actually it's not. How about this guy over here? How do you want to classify him? It's the same setup here. That's an empty p orbital, cyclic conjugated. Let's say check for now. How many pi electrons in the system? 4 pi electrons. What do we have? Anti-aromatic. What's the stipulation? If planar. You think it wants to be planar? Why would it want to avoid being planar? Because it doesn't want to be a cyclic conjugated diradical. The question is, does it have enough flexibility to become non-planar? Actually, not sure. The smaller the ring, the less flexibility it has to kind of become non-planar. What we certainly know is that an aromatic cation on the right. It's certainly not an aromatic cation. We know that. Okay, so the if planar part is important. Now, how could you tell if this was anti or not? A little bit hard to tell, but you would judge its stability. I mean, if you can somehow form it and do NMR, you could maybe tell is it aromatic signals or is it alkene signals? It's a little bit harder to tell anti versus non. Certainly not aromatic. Which one of these cations is going to be easiest to form? The left or the right? No, much easier to form. For example, if we look on the other page, here are 2 substitution reactions. Both alcohols, seemingly very identical. One of these is very easy to do, HBr, substitution. One of these is very difficult, pretty much does not happen. Somebody tell me what? What's the mechanism here? Probably protonate. And what's next? Mark?
Ionize?
Yeah. I mean, you could possibly envision SN2, but this is probably going to be SN1. Ionize. If you ionize, what do you make here? And is that carbocation going to be easy to form?
Yeah.
Yeah, we just showed it. Yes. What about this carbocation? Protonate ionize. Is that going to be easy to form? No, we just showed why. Here, your intermediate's going to be easy to form. There, you're going to have to keep waiting because it don't want to form. Or, it all depends on aromatic, non or anti. It's certainly not going to be as fast as this one. This one's going to be eager to form. Aromatic. Okay, so those are anions and cations. There should be problems in the workbook. I know there's like at least one MO problem in the workbook. Of course, you got your textbook. Next topic is going to be heterocyclic or heteroaromatic compounds. This is benzene with a nitrogen instead of the CH. We've seen it before, pyridine. Please take a look at these. I went ahead and have drawn in sort of the orbital diagram for us. On Wednesday, I will see if there's any questions about these. Okay? Have a good day, guys. See you soon.
Next year,